Welcome to day 10 of the Advent of Code 2022. Today we're building a simple CPU simulator to help fix the screen on the communications device that we've broken on the fall into the river. So we've got two instructions we can implement. The first one is no op, so no operation. It runs for one CPU cycle and doesn't do anything. We've also got addx, which takes one argument. That takes 2 cycles to run. So the first cycle, we don't see any change. The second cycle doesn't make any changes visibly, but it does update at the end of the cycle the value of our single register called x, so that by the next cycle, after addx finishes, our register has been updated to be the value of the register plus v, where v can also be negative. So we've been given some examples to show us what the state should be at each step, because you've got to be careful about what cycle you're on, and therefore what value v should have. And then the problem we're being given is after 20 cycles, 60 cycles, calculate the cycle number times the value of v, and then the sum of all those values, which is the sum of all of our signal strengths. So the idea is that based on v, we're sending some signal to the screen, and we're going to try and work out what that is, probably to use it in the second part. But let's get this bit done first. The first thing we're going to need is some idea of instructions that can be executed. So we're going to introduce some Rust that we haven't used yet in this Advent of Code, which is a trait called instruction. This is going to allow us to add some behavior to both of our instructions. So we'll add a do work function that takes a reference to self and the value of the register x, and we'll make that mutable so that it can update it if it needs to. And it's going to return a boolean to say whether the work of this instruction is finished. So let's add our no-op instruction first. So we'll add that as a struct called no-op instruction. And that's going to track how many cycles it has remaining. Then we'll implement that struct by giving it a new function, which returns self. So it'll be a no-op instruction with cycles remaining initialized to 1, because that's how many cycles the no-op instruction takes to execute. And then we want to add this trait behavior to our no-op instruction, the instruction trait. So we'll implement the instruction trait for the no-op instruction. That'll ask us to add the method. And from there, we can say if the cycles remaining has reached 0, then we're finished. Otherwise, we just decrease cycles remaining and say we're not done yet. And we actually don't need the register x because the no-op doesn't do anything to it. Then we want a second struct which represents the addx operation. This will again have cycles remaining, so we can copy that. There we go. And we also need to track the value that our addx is taking. There we go. And then we can implement that instruction. So we've got a new function for it, which takes a value and returns a self. That's going to be similar to this with the right name. And then cycles remaining will be 2, and we'll initialize v to be v. So that's just a shorthand for saying v : v. So that's our implementation, and then again we want to add the trait behavior to it. So let's copy our previous trait implementation, because it's going to be similar again. And this will be implement instruction for addx instruction. Here we do need the register. So we start with our cycles remaining at 2. We decrement. At the point we've reached 0, we've done 2 steps. We've been called a third time to check if we're done. And at that point, we can update the register. Okay, so that's our instructions. Now we can move on to building the CPU for these. We have a fair bit of work to do here, so let's get into it. The first thing we want to do is track the instruction that we're currently working on. And for that, we're going to need to start with an instruction. So we'll just start with a no-op instruction, construct it. So that will be fine, but we want to be able to store either a no-op instruction or an addx instruction in this variable. So the simplest way to do that will be just to create a box. So it's a simple pointer, and the pointer can have a known type, which is just the instruction. And that will need to be marked dynamic. So we don't know exactly what's in there, but we know that it's something of type instruction that we can call do work on. We don't have to know what the underlying type is. We don't want to have to deal with waiting for that no-op instruction to execute. That will mess up our program. So let's just run that through first once. And that needs our register, so let's grab that. Register X starts at 1. We know it's safe to pass off to this because the no-op doesn't do anything. There we go. Now we can start our loop. So let's just start with a loop. And the first thing to do is to try and execute the current instruction. So current instruction do work with andmut register X. Now there's two cases here. Either this returns false and we should carry on doing work with this instruction, or it returns true, it's finished and we're ready to load a new instruction. So let's deal with the case that it returns true and we need to load a new instruction. So in that case we can load the next line. So that line is not necessarily there, so it's there when we're reading the file. When we reach the end of the file, it won't be. So if let sum next line, equals next line, and we'll call that instruction. Otherwise, and we'll handle that case in a moment. So we can then match our instruction name. So we know that both no-op and addx are the same length, which makes this easy to extract. So in the case that it's no-op, we need to build a new no-op instruction. Build a new pointer to no-op instruction, new. Then we need to update the current instruction to be box new of addx instruction. Build one of those. That's built from the instruction. Select out characters 5 onwards. Parse those as a number. And unwrap the result. And it's not quite happy. So the parse shouldn't have been called there. That should sort it. Okay. And otherwise we need to handle the case that the instruction doesn't match. We'll just panic here and just say unknown instruction. There we go. So if we load in a new instruction, because of the design of this CPU, we don't take time doing that. We don't count a cycle for that. So we just want to continue here. So we'll jump back around our loop and immediately try and run that instruction again. If we are out of lines to run, then we want our program to stop. So we'll say end of program. It's false to start with. Then we'll switch this to a while loop, while not end of program. And then we can update this here to say end of program. So we could just break, but we're going to want to run some logic after this. So next thing to do is to track our cycles. So let's do that up with our register because that's part of our CPU. Start at cycle 1 and then increment our cycles as we finish each loop. So what we haven't tracked yet is the final output. So the way to do that is going to be to check if cycle minus 20 mod 40 is 0. So we're trying to check the 20th, 60th, and so on instruction. So the gaps between instructions are 40, but we don't start until instruction 20. So subtracting 20 and then checking if it's divisible by 40 is a quick way to check that we're on one of the instructions we care about, or one of the cycles we care about. And then we need to track our signal strength. Signal strength total is 0 to start with. Then we can update it here by adding the cycle number times the value of the register. And then finally, we can print out the result. Part 1 monthly signal strength total. Let's run that and see what it gives us. So there was a slight bug there. I've just fixed that. Let's cargo run again. And it's saying 13,140. So that's the correct answer for the sample input. Now let's run it again with the real input. And that's giving us 12,840. So let's see if that's the right answer. So what's this saying? Correct. Excellent. So on to part 2 then. So for part 2, we're going to implement a simple CRT monitor. So we're being asked to render a sprite that is 3 pixels wide. And now our register X will tell us the middle of that sprite. So as the CPU runs, it's going to drive the CRT, and the CRT is going to print a pixel at a time. So for each cycle, we will either print a hash if the sprite is visible, or a dot if the sprite is not visible at that point in time. So both the CRT and the CPU and the instructions are all going to be updating at the same time. So we just have to follow some simple rules. So to say that if the register X is within 1 of where the CRT is currently drawing, then we will print out the hash, otherwise we'll print out the dot. So hopefully not as difficult as it looks. And then once we are done, we can print out each of those lines that it'll draw as it runs, and that should draw some letters on our terminal. So let's give that a go. So there's enough code in the implementation of this CPU that we don't want to go copying it. So let's just add the logic for part 2 into what we've already done. So first thing we're going to want is something to keep track of our CRT. And we'll use a string. So it's fine to be appending characters into a string. It's designed to cope with that. It's not going to perform too badly. So then we need our logic. So let's figure out what the CRT position is. So the CRT position runs from 0 to 40. So, or from 0 to 39 really, or 1 to 40, depending on how you think about it. So to figure out where we are on the line, let's take the cycle, which is 1 based, and convert that to 0 based. And then we can mod this by 40. So that will then give us our line lengths. So now if our register is in the same place as the CRT, or rather if the register is close to the CRT position, so if register -1 is within the CRT position, and the CRT position is close to register +1, so that's the width of our sprite being accounted for, then we can add to our CRT line a single hash, and otherwise we'll print a dot. Okay, and then if we're after the first cycle and our CRT position is at the end of a line, which is 39, then we can print out the line we've currently built, CRT line, and then we need to reset that CRT line to start building the next one. So that doesn't need any printing at the end. That should print out our answer as it runs. So let's see if it does. Right, how does that look? Okay, they certainly look like letters, but not very easy to read. So I'm thinking Z, K, J, F, B, J, F, Z. So let's put that in and see if that's the right answer. Okay, so reading back off the terminal, we had Z, K, J, F, B, J, F, Z. So is that the right answer? Fantastic. So that's the end of day 10. I will see you tomorrow for day 11.